let's finish up section 1.3, part 2. So we're going to start out with a function called the greatest integer function. It's a very, very simple function. And the definition is, you give me a number, and I'll give you the biggest integer I can that's less than that number. That's the greatest integer function. Less than or equal. Right, so you can plug any number in, and what gets returned to you is the biggest integer possible that's less than or equal to the number you started. And there's a couple different symbols you might see for it. You might see these double parentheses or double bracket kind of things. When we're doing it on the calculator, we're going to look for this symbol called INT. Right, so if I gave you an example, if I plugged in 2, what's the biggest integer you can think of that's less than or equal to 2? Yeah, Annalise?
1.9.
It has to be an integer.
Oh, 1.
I can think of an integer that's bigger than 1.
Would it just be 2?
It would be 2, but less than or equal to 2. How about if I said 2.3? What's the biggest integer less than or equal to 2.3? Yep. 2. How about 2.7? Yep. 2. 2.9. Yep. 2. 2.99999. 2. Then all of a sudden you get to 3, and it jumps up to 3. So what the greatest integer function looks like, it's almost like a series of steps. Right? When I said 2.1, you guys said 2. 2.2, 2. 2.7, 2. 2.99999, 2. Then when I get to 3, it jumps up. Okay, this is also known as a step function, because it looks kind of like a series of steps, where each step has a closed circle on one end, because you can include it. And here, 2 is not included in the first step. 2 would actually be included in the second step because of the way the integer function rounds. It's almost like just taking, for positive numbers, it's almost like just taking the number and just crossing that part off. No matter what it is, crossing it off. Now, you've got to be a little bit careful with negatives. Right? If you said like negative 1.5, what's the biggest integer you can think of that's less than or equal to negative 1.5? You think of a number line. Less than means it has to be to the left. So what's the biggest number that's less than or equal to negative 1.5? Yeah?
Negative 2.
Negative 2. Right, so it's a little, just got to be careful with that. So if you want to graph this on the calculator, I can't do the open and close circle thing, but I can show the steps. You press math, you go to number, and the fifth option down is int. So we're going to graph int x, just like it looks right there on the board. Int x. We'll do zoom 6. And you can see we get pretty much the same picture. I just can't properly show the open and closed circle. But you get those steps. Okay, any question on that? Yeah.
What would we use this for?
So one example of it would be like if you think about like if you ship anything from the post office, if your package weighs, say, 1.1 ounces, if it goes over 1 ounce, they charge you for 2. They always round up. So anything between, like, say they'd only measure to the nearest tenth. Anything between 1.1 and 1.9 ounces, you're going to pay the 2-ounce price. Actually, even right up to 2. You still pay the 2-ounce price. So anything from 1.1 to 2, you pay 2 ounces. If your package weighs 2.1 ounces, up to 3 ounces, you're going to pay the 3-ounce price. So that's an example of how the post office rounds up when you have to pay for shipping. All right, so I already did a complete graph. I would say negative 10 to 10, negative 10 to 10. Standard window is fine. But let's determine the domain and the range. Okay, so domain are the numbers you can plug into the integer function. What kind of numbers are you allowed to plug into the integer function? I don't want to know what the answer would be, just what kind of numbers can you plug in? Tim?
Real numbers.
Yeah, you can plug anything you want in. You can give me a positive, a negative, a fraction, or a decimal. So that's all real numbers. Now, what about the range? What kind of answers do you get? Yep.
Only integers.
Integers. It does go up forever and it does go down forever, but you'll never get a value of like 2.3 from the greatest integer function. The value returned to you is always an integer. So the range, all integers. That's kind of a weird range. We don't normally have something like that. But that's also kind of a weird graph. We don't normally have steps like that either. All right, let's try another one, just practicing another domain and range. So, first of all, we can usually get the domain without a graph. Do I have any square roots in that problem? Nope. Do I have a fraction with a variable in the bottom? So then most of the time that means the domain is going to be what? All real numbers, and it is. You can take any number you want and raise it to the third power. Positives can be raised to the third power, negatives, decimals, anything can be raised to the third power, even 0. It's fine. Range is usually a little harder, and that's where the graph can be helpful. So I'm going to type in 16x minus x cubed. And I'm going to start with zoom 6. All right, it looks like it's going on off the screen a little bit on the top and the bottom. So I want to zoom out a little bit, set the y max and the y min a little give me a little bit more range so I can see more. Let's try like negative 40 to 40. Because it was going off the screen before. Hopefully now it doesn't. Okay. So this is very typical of what you call a cubic function. Right? When you have a parabola, the exponent is a 2. And when you look at the graph of a parabola, the exponent is a 2, and the graph takes 1 turn. When you have an exponent of 3, the graph can take up to 2 turns. But that's it. It can never turn again. Okay? So the highest exponent, if you subtract 1 from it, tells you how many times the graph can turn. Can turn, doesn't have to turn. Okay. This one does turn 2 times. I can see both turns, which means from here, that just continues down, and that just continues up forever. So what does it look like the range is in this one? Negative infinity to infinity, yes. If you weren't sure, you can zoom out even higher, but you're not going to see anything different that you're not already seeing. Negative 100 to 100, hit graph. It's still that shape where it turns twice. Now you're seeing 200 units on the screen. But it's just going to, this will continue down, and that will continue up. Okay, so for a polynomial, subtract 1 from the highest exponent, and that'll tell you how many times the graph could turn at most. All right, just like that and that. Okay, so let's look at this. So it's a word problem. And I just kind of wrote down some of the important things. It says we have a rectangular pool with dimensions 30 by 50. There's a sidewalk around the pool. That's the same width all the way around. And the area of the sidewalk is 600 square feet. What's the width of the sidewalk? Okay, so we got a lot of information here kind of in a sentence format. And we've talked about different strategies to solve problems. What would be a good strategy, you think, for this problem to help us kind of interpret this information a little easier? Yeah?
To draw it out.
Yeah, let's draw it out and see what it looks like. So the first thing I'm going to draw is a rectangular swimming pool. Right, so let me draw that. All right, so here's my pool. And around the pool, there's a sidewalk. So what I'm going to do is just make a sidewalk around the pool, just like that. So there's my sidewalk around the pool. Now I know the pool is 30 by 50. So we can put 30 by 50. And there's a sidewalk around the pool that has a width of x. So this width, I'm going to put it outside. I'm just trying to put it in a spot that doesn't look confusing. So this width of the sidewalk from here to here is x. And that width is the same on all sides. Okay. So they want to know the width of the sidewalk. That's what we're solving for. All right, so the shape we're dealing with is a rectangle. And in the problem, they definitely give me some areas. So I'm going to need to remember the formula for area of a rectangle. What's the formula for the area of a rectangle? John?
It's length times width.
Length times width. Okay. So what we know is this area. Right? That's the area of the sidewalk. We know that. How could you find the area of that sidewalk if you knew the area of the big rectangle and the small, well, we'll say the pool, right? Like the big rectangle and the small rectangle. Yeah.
Subtract the big rectangle's area minus the small rectangle's area.
Yeah. So the area of the sidewalk is equal to the area of the big rectangle minus the area of the pool. Now we just need to fill that equation in and solve it. And that's our answer. What's the area of the sidewalk? Yeah.
600 feet.
600 square feet.
Yeah.
The area of the pool, we know that that's 1,500. They didn't give us that, but we can do 30 times 50 and get that. Now the area of the big rectangle. Remember, length times width. How long is the length of the big rectangle? I'm not going to have a number, but we're going to have an expression. Yep.
Would it be 30 plus x squared?
It would be 30 plus, not quite x squared, but yeah, 2x. 30 plus that little part plus that little part. So 30 plus 2x. And likewise, my width would be, well, we did them in reverse, but that's okay. So 30 plus 2x, I meant to say length, I did width. But now 50 plus x is my width. Okay, so 50, x, and x. All right, so now let's simplify that and see what we get. So 600 equals, remember those parentheses need to be FOILed, the double distributive property. So 1500, that's going to give me plus 60 plus 100x. So 60x for the outer, 100x for the inner. 60 and 100 is 160. 2x times 2x is 4x squared. So I ended up with 1500 from the foiling, plus I had the 1500 for the pool. That's gone. Now, what I have is a quadratic. Usually when we solve a quadratic, what do we try to get it equal to on one side? 0. So let's put everything on the right. If I put everything on the right, well, 0 is on the left. And let's put it in descending order. So what would be my first term in descending order? Caleb?
4x squared.
4x squared. Okay, got that. What would be my next term in descending order? Yep, Lindsay?
Plus 160x.
Plus 160x. Okay, we got that. And now what about the constant? What would be at the end? Yep.
Plus 600.
So that's going to be coming over from the other side. So what would happen to it?
Oh, minus.
Minus 600. Now, just to make these numbers a little easier to work with, what is everything divisible by? Yep.
4.
4. So if anytime you can divide it through by a number, that'll make it easier to solve. So there's the quadratic equation that I need to solve. That doesn't factor, just because I remember the answer doesn't come out to a nice number. So if you can't factor a quadratic equation, what's the other way you can solve it? This method is the method you have to use when it doesn't factor. Yep.
The quadratic formula.
Yep, quadratic formula. So, I'm going to have negative b plus or minus the square root of b squared minus 4 times a times c. And what is it all divided by? Anyone remember? Yep, 2. In this case, 2a, but a is 1. Remember, a, b, c. So let's check it. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Minus a minus, that's going to turn into a plus, because it was a minus. And when I distribute that out, it would be a minus as well. So we have negative 40 plus or minus, let's see, what's 4 times 150?
600.
600 plus 1600. How much is 600 and 1600?
32, no.
2200. So 2200 divide by 2. And that is the exact answer for the width of the sidewalk, but it has a plus or a minus. Well, the sidewalk can only have one width. So that means one of these answers probably won't make sense. What type of answer would not make sense for the width of the sidewalk? Okay. A negative. So I'm not even going to bother with a negative number minus another number divided by 2. because I know it's going to be a negative. I'm only going to look at the positive. Negative 40 plus the square root of 2200. Divide by 2. So negative 40 plus the square root of 2200. And divide by 2. And that means the sidewalk is about 3.45 feet. So that's approximately. All right, so definitely setting up a picture and then kind of figuring out this equation. This is kind of like the big idea of what you're trying to do. Figuring out like the geometry of it. What do you have to do from there? And then actually plugging in expressions for each one of those. And sometimes it comes out to a quadratic like it did in this case. Any question on that one? All right. So projectile motion. So this is something that we'll study quite a bit. If you didn't know the formula for a test, I would have this on the test for you. But projectile motion, it's basically like the motion of an object traveling in an arc, like a parabola. And how that object is going to travel in an arc really depends on three things. So let's say, I threw a football or baseball, and I said, how high is the baseball? Well, you'd have to know a few things. First thing you'd have to know is how high is the baseball at what time? 2 seconds after I throw it? 5 seconds? How much time has gone by? The other thing you'd have to know is how hard did I throw it? When I released it, how fast was the object going? And the second thing, or the third thing you'd have to know is what was the initial height? Was the initial height like my height when I released it? Was it as high as my head? Or did I throw it from off the top of a building and it's going to come down to the ground? In that case, it had a lot more initial height to start with. Anytime you see a problem that says ground level, you can assume the initial height is 0. It says an object was thrown from ground level. Yeah?
I'm just trying to like in it. Did it literally just mean throwing it from like the ground? Like how would that work?
Yeah, or like a rocket that started on the ground. Yeah, so you've got a rocket, and you're going to press a button and it's going to take off. It's starting on the ground. So the formula is negative 16t squared plus v sub 0 t plus s sub 0. This formula is important. It does require you to use feet and seconds. If anybody of you are in physics and you see the number negative 9.8 here, that's a number you will see a lot. That's assuming you're using meters. When we have the 16 here, it means feet. Let's try an example. So this says a rocket is shot straight up from ground level with an initial speed of 64 feet per second. So maybe it's like one of those water-powered bottle rockets. You pull the cord and it takes off. There's no engine on the rocket to keep it going. So at what time will the rocket be 50 feet above the ground? Okay, so let's see if we can solve it. Let's use that formula and fill in everything we know. They're telling us height. They want to know when the object is 50 feet above the ground. The height is s of t. That's the height right there. So in this case, 50. Negative 16t squared plus v sub 0 t. What's v sub 0 in this problem? That's the initial velocity.
64 feet, sorry.
64 feet per second plus s sub 0 is the initial height. what did they tell us the initial height of this rocket was?
Ground level.
Ground level, it says it's, yeah, ground level. So plus 0, I don't even need it. Now, what kind of equation is this again? Yeah.
Quadratic.
It's another quadratic. So I could go through, do the quadratic formula, all that fun stuff. I've already done it that way once. Let me show you a different way to solve a quadratic if it doesn't have to be done algebraically. We're going to take and put what's on the left in y1. So I'll put what's on the left in y1. We're going to put what's on the right in y2. I'm going to adjust my window, but when I hit graph, what do you think I'm going to look for? Yeah. I'm going to look for an intersect. So I'm looking for where the rocket hits 50 feet above the ground. So my y max should be at least 50. I've got it at 100, so that's probably enough. Is this object ever going to go below ground? No. So the lowest I ever need to worry about is 0. And remember, x is how much time has gone by. Can negative time go by? No. You can start at 0. How much time can go by? As much time as you want. Eventually, the object is on the ground, and then it just stays on the ground after that, because it comes up and it goes back down. So, let's hit graph. There's my line at 50 feet. There's the object. And in this case, the graph is almost a pretty good picture of what it would actually look like. It's going to hit 50 feet on the way up, and it's going to hit 50 feet on the way down. So when does the object hit 50 feet? Well, 2 different times. The first time it hits 50 feet is second calc intersect. Let's pick a point. Blue, red. Do my guess. I have to have my guess closer to the left. It's about 1.06. So approximately 1.0 seconds after it's launched, it'll hit 50 feet. Yeah.
It's somewhere in another dimension.
So is one of your scatter plots highlighted at the top?
Yes.
Okay, so just go up to the scatter plot and hit enter, and that'll turn it off.
Okay.
I have to go now back up now and turn it off myself.
Okay.
Now let's do second calc intersect again. Since I turned a scatter plot on and off, it has to redraw it. If I hadn't done that, it would have still been on the screen. Alright, so now second calc intersect. Now if I just hit guess right there, it should be fine, because it's definitely closer to the intersection point on the right than it is on the left. And that's perfect. Yes.
So if we were to do the quadratic formula, the plus or minus both would have turned out to be positive.
Correct. This time when you have the plus or the minus, they would both come out to be positive, and you would want to write both of them down, because in this problem, they both make sense. In the width of the side block, they don't. But those are your 2 answers. Now the last part, kind of showed you this a little bit in the homework, but it says, what is the maximum height and when does it occur? Well, we did a minimum. I think it was a minimum at -3. Well, maximum, it's kind of the same idea. You can basically do second calc maximum. Pick a point where you know, okay, I'm on the blue curve. That's not going to help me. I don't want to know the maximum of the blue. I want the red. Okay, hit the up arrow. Now I'm on the red. So pick a point that I know is to the left. Pick a point that I know is to the right. Hit enter. And now we have to interpret what that means. And remember what I said about this value. Sometimes it's just an estimate. So that's when it occurs, and that's what it is. So when do you think the maximum occurs here? At what time? How long?
1 second.
1 second? So 1 second, the object would be
Oh, 3.
about right there. Yeah, this is at 2 seconds. Okay, it is 2 seconds. It's not 2.000000006. It is 2. So the maximum is at 2 seconds. And what's the height of the object at 2 seconds? Yep.
64.
Yeah. So 64 feet, and that occurs at 2 seconds. That answers the question of what the maximum height it is, and the time that it occurs at.
Mr. Hager,
Yes.
how come we did the same exact thing, but I got 1.999998 for x and you got 2.0006?
So it's just a matter of how the calculator is doing that. It's guessing millions of times per second, and it could be a difference in the operating system. They could have updated the algorithm that yours uses versus what mine uses. And even though our results are the same, it's a slightly different method the calculator is using. So you get a slightly different answer when you go out like 10 decimal places. But that's the only thing I can think of. Something in the programming is a little different between yours and mine. Most people that are using the ones in here, one of my calculators, did you use one of mine?
No.
No? Okay.
I have the same calculator as him, and I got the same answer as him.
Okay, so you have the same calculator. So it makes sense if you have the same calculator model, it's going to do it the same way. My model might be a little, yours looks like it's newer than mine. I think mine's a TI-84C. Is yours the CE?
Yes.
Yeah.
Yeah.
So they maybe updated it a little bit. That's all. Yeah, that's a good question. I think it just comes down to programming. All right, and then the last thing in this part is called what's called a piecewise defined function. The important thing is I want you to just understand how to type this in on a calculator. So with a piecewise function, you basically have two formulas you're graphing on the screen at the same time. When you write something like this, you can plug in any value for x you want. It's not like it says, okay, use this formula if x is odd, use this other formula if x is even. You use the same formula for everything. Well, in a piecewise function, you don't. Usually you're given two or more formulas, and you're given a condition when to use that formula. So you might have a formula that says use formula 1 if the value you want to plug in is less than 0. Use formula 2 if the value you want to plug in is more than 0. It's like two different formulas. So there's a different rule for each part of the domain. And you could split it up even more than that. You know, maybe use this formula if you want to plug in a number between 1 and 10. Use this formula if you want to plug in a number between 11 and 20. And use this formula between 21 and 30. But this is what a piecewise defined function looks like. It starts with this bracket. And in this one, they give me two formulas. The instructions are to use the top formula for values less than 1. And the bottom formula for values greater than or equal to 1. So it involves a little extra thinking. If I said, okay, I want you to tell me what f of 5 is. First step is to figure out, okay, does that go in the top one? No, 5 is not less than 1. Does it go in the bottom one? Yes, 5 is greater than or equal to 1. It has to fit somewhere. If it doesn't fit anywhere, that's the problem. Okay, but it does fit into the bottom one. So now let me show you how you graph it. To graph a piecewise function, the big difference is 1, you have to use parentheses, and 2, you have to type in that condition. So this is how you do it. The first part is pretty much the same. The only difference is we're going to put 3 minus x squared in parentheses. And now next to it in parentheses, I'm going to type in a condition. X, and I don't think I've ever used the less than sign, so let me show you where it is. You press second, and you press math. All the inequality symbols are in a menu called test. Second, math. I want 5. Close parenthesis. So let me graph that and just show you what it looks like. Let's do zoom 6. You're going to notice, and the calculator can't quite do it perfect, this part shouldn't be here. That part that I just highlighted in red, it shouldn't be there. Because this graph should just stop when at less than 1. So the only thing you really should see here, if I make this the same color, so you can't see that anymore, that's what the graph should look like. It's a graph that just stops at 1. And then this other graph is going to take over, but I haven't typed it in yet.
Where's the inequality again?
Well, let's do the second one. So we're going to need an inequality symbol again. First, I'll just type in my graph. Now, notice here how my cursor is still blinking in the exponent. The minus 4x is not up in the exponent. So I have to hit the right arrow. So when I type the minus 4x, it doesn't go up in the exponent. It should look just like that. Now we're going to put parentheses, x, and the inequality symbol is under second math.
Oh, okay, thank you.
And this time I want inequality 4. Remember, anything that it draws on the axis, we don't want to look at that. I can't turn that off. There is no way to get rid of it. But when I hit graph, this is what the actual graph should look like, and just pretend that that axis is black and you can't see that part. Now, technically, on the end of the blue graph, would that be an open circle or a closed circle? So this was the blue, and this was the red. So what kind of circle on the end of the blue? Yep.
Open.
Would be open because we don't include 1 on the blue graph. That's strictly a less than. Calculator can't do that. And what kind of circle on the red? Should be closed because on the red graph we can equal 1, so we can include it. That's perfectly what the graph should look like. So that's called a piecewise function. It's just really 2 graphs or more on the screen at the same time. Any question on that? So I think some of this is probably new. I'm sure graphing piecewise functions, the step functions, that's why I wanted to go slow through 1.2. What did we just do? We did 1.3. 1.4 is a complete review. So I don't really like to spend a lot of time on it. We don't have a lot of time anyway. But it's all like y equals mx plus b slope. I'm going to put the formulas on the board if you need them. And they'll be in the video because I'm going to go through it. But we're not going to really go through lots of examples. Okay, so again, from Algebra 1, hopefully this is all review. Anything you don't remember, feel free to write it down. But y equals mx plus b, that's the slope-intercept form of a line, where m is your slope and b is your y-intercept. Most of the time we write linear functions in the form y equals mx plus b. It's not the only way, but it's a way that we use quite a bit. In this type of formula, the m and the b could be positives, negatives, fractions, decimals. Generally, yeah, it could be all those different numbers. We're going to skip that. So the formula for slope, if you don't remember slope, it's Some people remember it as two words, both beginning with an R. Anybody know what I'm thinking of? Yeah?
Rise over run.
It's rise over run. And the way you calculate rise is subtract the y's. Rise, y's. And run is a horizontal distance, so we subtract the x's. Okay. There are two special cases of slopes. If you have a line that's perfectly horizontal, that's a zero slope. And if you have a line that's perfectly vertical, that's an undefined slope. And so those are special cases. So I said to you that most of the time we write equations in y equals mx plus b, just like there's two special cases of slope. There's also two special equations for those types of lines. Y equals a number, that's a perfectly horizontal line. X equals a number is a perfectly vertical line. So, just because this one's pretty quick, what would be the equation of the horizontal line? I already started it out for you. That goes through the point 2, 3.
That would be y equals 3.
Yeah, y equals 3. If you put a horizontal line at 3, it would go through the point 2, 3. And what about the vertical line that goes through the point 2, 3? Yep, x equals 2. There's really no calculation there. Horizontal and vertical lines are a special case. They're not y equals mx plus b. So something like this, you should be comfortable taking 2x plus 3y equals 6 and doing this to it. That's rewriting it in y equals mx plus b form by getting y by itself. Why would we do that? It's easier to graph. So that's important. Point slope is another way you can write the equation of a line. I don't use it a lot unless they give me a problem that says write the equation of a line and they give me a point and they give me a slope. Then I'll use it. But other than that, if I'm writing something as a final answer, my default option is y equals mx plus b. Again, unless I'm told not to do that. Right, so in a problem like this, find the equation of a line with a certain slope and a certain point. Well, that's perfect for point slope. They gave me a y1 and an x1, and they gave me a slope. So I would use that formula. This type of equation of a line isn't used much. It's called standard form. We do this more when you have a quadratic. We get it equal to 0. You can do it with a linear equation. It's just basically moving everything over to one side of an equation. I hardly ever use this. If two lines are parallel, what does that mean? Actually, it means two things. They would have what?
You would have the same slope and a different y-intercept. Well, yeah, like y-line.
Yep, same slope and different y-intercept. Does anybody remember if they are perpendicular? Something about the slopes. It's not same slope.
It's a negative reciprocal.
Yep, it's the negative reciprocal, or sometimes we call that the opposite reciprocal. So you might see a problem, or you will see a problem. Something like write an equation that's parallel to this one and goes through this point. So the key to remember is if it's parallel, you have to have the same slope. So you'd have to find the slope of this. How do you get the slope of this? Get y by itself, just like I did in the other one. I think. Okay, graphing linear inequalities. We could talk more about that tomorrow, but people remember maybe doing something like this and then shading on one side of the line. So the quick way to do it is you basically have to graph your line. It's dotted or dashed for these two symbols. It's solid for those two. And if it's a greater than, like if I said to graph y is greater than 3x plus 2, greater than means you would shade above. Less than means shade below. Usually you end up shading on one side of the line. You can also pick a test point. Some people do it that way. They pick a point above, plug it in and see if it works. If it does, shade above. If it doesn't, then shade below. I usually just remember greater than is above, less than is below. That's pretty much it. So on page 42, these are going to be a lot of little quick questions, like find the slope, find the y-intercept, stuff like that. Okay, page 31, that's the newer stuff, and that's why I spend most of the time on that. All right, so if you remember the y equals mx plus b, I think you're going to find page 42 takes you 5 minutes. It's a very, very easy, very fast page. Page 31 might take you a little longer because it does have some graphing calculator stuff.
How would you prefer that we show that in our work?
So when it says find a complete window, I'd like you to write down like the mins and maxes that you used for the window. If the directions say sketch, that means actually draw a little sketch on paper. Okay. I think there's a question in the homework that says sketch and use a graphing calculator to confirm. So I'm going to look that you drew the picture. And then if you confirm it, I mean, that's up to you if you want to do that on the calculator. But yeah, some things if you're not sure, if it's a calculator question, always ask you the next day. Because pretty soon you'll start to figure out what they're looking for. But some things, yeah, you can just write, I did that one on the calculator. There's really nothing to show on paper for some things.